welcome. So, in this lecture we are going to talk about MATLAB model development for mixed signal current mode control. So, we will first talk about custom MATLAB model development and then we will take few simulation case studies. So, this is the architecture that we have discussed in detail in the previous week, and we are starting from this known mixed signal control architecture where the current loop is in analog and then you have a voltage loop which is in digital. So, first thing we need to understand the waveform here. So, here we know that if we take the sample here and we know it requires some time for the conversion and computation, and then the peak current will be ready, and that time we will actually start the switching process. That means, the switching clock and the sampling clock, there is a delay, and in order to implement that we have understood particularly this clock control compensator has to be clock synchronized. It should not be a simple transfer function. So, we need to use a difference equation, and that we have discussed in the previous two classes. Okay. So, we want to use the same approach, but now in this case we will use a PI controller rather than PID controller because it is a current mode control and we need to implement this. Now, we will have A to D converter, and we have already discussed the implementation of A to D converter, which is a quantizer block and then sampling block. The sampling block is we can make event trigger sampling that we have discussed earlier. Then you can use a quantizer block and we can add a delay. So, this is an event trigger sampling. We know it is an event triggered sampling, and we can use with respect to any clock. Event can be a simply clock, or you can create a virtually any event. Then we can generate the error voltage. So, after this block, delayed block, that means this represent this whole block represent our ADC. Output of the ADC is the V0 n, then this is error amplifier block. Then it goes to the controller and is a PI controller, and we have discussed this PI control implementation using a clock synchronized difference equation. That means, here this will be implemented using a clock synchronized block, and let us go to the MATLAB block. I will just show. This is a mixed signal architecture. Here the power stage remains same, but the controller is different. And if you go to this block, this is our A to D converter. Then here is the PI controller. If you go inside the PI controller, then what we will see that this will generate. So, this is the overall error voltage. This is simply the proportional controller part plus integral controller part. So, this is a Kp into error voltage plus integral Ui of n. How to generate Ui of n? Ui of n will be generated from, that means it is nothing but K Ui of n minus 1 plus Kd into error voltage, Kid, that is a Ki, basically the discrete time integral gain, and this go to a go to block. So, this block actually create a delay. That means, this block input to this block is Ui n and output to this block is Ui n minus 1, and that is used here. Okay, this is used here, Ui and Ui n, and this delay is created with respect to this clock. That means, this clock will actually synchronize with the delayed error, the integrated output. And if you go up to the controller, and then rest of the blocks like your typical current sense, then this is a reference current, peak current. So, that means, this is the block that we have discussed, G of Z. Then DAC, that means it is, you can also put a delay if you want to additionally consider the controller delay. Then DAC is simply, you can add a quantized block here. In fact, this digital controller is quantized itself. So, DAC may not need another quantization. So, only the DAC bit size should match the quantized level that you are sending. But if you say a lower resolution DAC, then you may have to create another quantization block here. Then it goes to the reference current. The reference current is compared with the inductor current. This is the comparator. Okay, so this is the comparator. This comparator is here, and output of this comparator goes to the SR latch, and the SR latch, it will be set by the switching frequency clock, it will be reset by the comparator output, and this is under trailing edge modulation that we have discussed. So, if we just look at the current mode control implementation, if you remove this digital part, then it is exactly same as analog current mode control, because it is analog current loop, and we are just generating the reference current through a digital controller, where this is the reference current generated from the output PI controller output, digital PI controller, and you need a A to D converter. Okay. So, now we want to run the simulation case study. Now, we want to first use a load step size of 20 ampere load step. So, we can again change the whatever we want to change. So, here I am showing the load transient response. We have not yet discussed about the design of current mode control. This is just with an arbitrary set of PI controller, and you can see that this is the sample voltage. Here we are using the sample point same as the switching point, but suppose if we want to adjust this, so we have to just delay this clock. That means we can use this block to be, let us say 0.9, and I will show you that the clock, it will be delayed. So, I just want to show that now the sampling is happening first before switching. So, that means you can customize the sampling process, and this will help to accommodate the conversion time and computation time. So, you can implement current mode control very effectively using MATLAB simulation block. So, that means A to D converter. So, everything that means is all set. So, you can implement any mixed signal current mode control architecture. Now, in real time, we can also update the controller gain, which is this gain, so that you can do some tuning method in real time, or you can use a large signal based controller tuning, that we will discuss when you go forward, but the design is not yet, we are going to discuss design in a separate week. There will be a dedicated week for design. So, in summary, we have discussed the overall implementation of mixed signal current mode control. So, we have discussed custom MATLAB model development for mixed signal current mode control. Then we have considered few MATLAB case studies. So, I want to show one more thing here, I forgot, because in current mode control has excellent line regulation. That means, if you take about the supply transient, we want to see what happened with the supply transient. That means, I am just making a 5 volt step down. That means, supply is changing from 12 to 5 volt, and see what happened. You can see, unlike in voltage mode control, here almost the effect is negligible. There is almost no effect, because current mode control has excellent audio susceptibility as well as line regulation, and that is why you can hardly see any transient effect here. Similarly, if you want to do reference voltage transient, that means I can use simply 0.05, but I can reduce the gain, controller gain. So, we have not yet discussed the design. So, here, yeah, this is the reference voltage transient. So, you can see the output voltage is changing from 1 to 1.05. Okay. And here we have used continuous time integral gain, continuous time proportional gain, and we have converted into discrete time. Proportional gain will remain same. Integral gain, there will be multiplication with t. The discrete time integral gain is a sampling time into the continuous time integral gain. So, that means we have discussed few case studies, and that means we have considered few case study using mixed signal current mode control. So, we will consider fully digital current mode control in the next lecture. So, I want to finish it here. Thank you very much.